All right, so now what we're going to look at is finding the electric potential energy and also using the conservation of energy when it involves electric potential energy. And so our first example is we have a charged particle moves in an electric field. All right, so I'm going to just draw that right away. I'm going to have our positive plate here. All right, there it is, and then I'm going to create electric field. So let's use some green arrows because again it goes away. All right, so there's our electric field. Okay, now A, it says for a proton, which has a charge of 1.6 times 10 to the negative 19 coulombs, calculate the change in electric potential energy when the magnitude of the electric field is 125 newtons per coulomb. The starting position is 2.5 meters from the origin, and the final position is 4 meters from the origin. All right, so what we have here is a proton. So there's our Q value, which is again 1.6 times 10 to the power of negative 19. We know we're going to put that proton in here. All right, so it had a distance here, it said, of 2.5 from the origin. And then it is moved out to 4 meters, to the 4 meter mark. All right, and we also, this strength of this electric field here that I've drawn in green is our epsilon, all right, which is 125 newtons per coulomb. And what we want to do here is calculate the change in electric potential energy. Now I have a formula for the change in electric potential energy that involves all these values, and that's something we looked at in the note there, where we have negative Q times epsilon times delta D. All right, now I know the charge, got it. I know the electric field, got it. And my change in distance here is, well, we've gone from 2.5 meters away to 4 meters away, and so that would mean our delta D will be 1.5 meters away. All right, so we've got everything we need. So if I'm going to find my delta E and substitute into my values, all right, so we have a negative sign there, a Q. Again, our charge is 1.6, it's a proton, 1.6 times 10 to the power of negative 19, times our epsilon, which was 125, and times our delta D, which we just moved it 1.5 meters more away. All right, so if I get in my calculator and I take those numbers and we multiply them, first of all, I got a negative times a positive times positive times positive. It's going to be negative sign. And what I get here is I've got negative, a very small number, 3.0 times 10 to the power of negative 17. And again, we're talking about energy, and so it is joules. So we've lost energy. And so what has happened is our electric potential energy, our EE, energy is used to speed up the proton. Right? Because again, these two positives attract each other. Right here, this positive plate and this positive charge attract each other, and so if you, they repel each other. Again, like charges repel each other, they repel each other, and so if you just let this positive charge go, well, it's going to speed up, but yet you're going to lose that electric potential energy tension between those two charges. And so again, because it's speeding up, well, that means our EK is increasing. Now, in terms of the conservation of energy, we have here, use the conservation of energy to calculate the final speed of that proton. And we're just going to, in this situation, assume the proton starts at rest, because a lot of times these particles are moving. And so again, conservation of energy, we have the change in our kinetic energy, which is going to be positive in this case because it's increasing, plus a change in electric potential energy, which we already proved is negative. We add those two, we got 0. All right, now a change in kinetic energy. Again, our formula for change in kinetic energy is mass times velocity, but in this case there's a change in velocity, delta V, which means we have our m, whoops, a little bit too big there, our mass, all right, times our change in velocity, which is Vf, minus Vi, and those are squared in our formula. All right, and I can't forget the divided by 2. So there's the change in our kinetic energy. And then our delta EE, let's see here, was negative. Oh, I might as well get rid of that positive sign there because it was actually negative. So plus minus. And so we have minus 3.0 times 10 power of negative 17 equals 0. Now the mass of a proton, we can look that up in the appendix. Oh, it's got it right there, 1.67 times 10 to the power of negative 27 kilograms. All right, so, and now the other thing is that our initial velocity, it starts from rest. So right here is 0. And so because it's 0, what I'm going to do is, well, just get rid of it. So our initial velocity is 0, and so all we got now here is our final velocity. All right, so I'm going to substitute in our values here. So again, our mass of our proton is 1.67 times 10, very small, one of the smallest particles we have around. All right, so 1.67 times 10 to the negative 27 kilograms. Again, we're in our standard units. Our final velocity, that's what we're trying to figure out here. Again, I can't forget the divided by 2. Minus our 3.07, or sorry, 3.0 times 10 to the negative 17. And again, it equals 0. All right, so here's what I'm going to do here. I want to solve for VF. So I'm going to move this negative 3.0 times 10 to the negative 17 over to the other side. And when it changes side, it changes sign. It's going to be positive. Now I'm going to move it over to the other side. So by doing this, put an equal sign there. And now there we go. I just switched it over to the other side, and it is now positive. And then I'm going to, let's see here, we multiply both sides by 2. Whoops, let's get that in red there to make it a little more clear. We'll multiply each side by 2. And so those 2's divide each other out. And so what we end up with here is, next on the page, we get 1.67 times 10 to the power of negative 27. All right, times our VF squared is equal to, well, 6.0 times 10 to the power of negative 17. All right, and then, well, I'm going to now divide, because I want to get VF by itself, so I'm going to divide both sides here by 1.67 times 10 to the power of negative 27. And again, when I do it on one side, I got to do the other here. There we go, and so those 2 divide each other out. And so let's see here, we get VF squared. I take those 2 very small numbers and divide them. So let's see here, grab my calculator. So I've got 6 times 10 to the power of negative 17. All right, and I'm going to divide that by 1.67 by the times 10 to the power of negative 27. And I end up with here, let's see here, 3 point, again to 2 decimal places, 59 times 10 to the power of 10. All right, but almost there. I got to get VF by itself, and so what I'm going to do is square root both sides. And I'm getting our final velocity of our proton, after we let it go from rest, to be 1.9 times 10, again, very small particles, to the power of 5 meters per second. There we go. So it's moving very, very quickly. Our electric forces are powerful, and this is a very small, small object, small particle. Proton's really small. All right, let's try another one of those. This time we're going to look at an electron. All right, so again we have a electron that is moving in an electric field. So once again I'm going to draw that. So we've got a positive here, a positive plate. It's always referring to a positive plate. All right, so we've got our negative charge. In fact, it's electron. Now these are attracted to each other. Okay, so let's see what happens here. So we have an electron, we have its charge. All right, we want to calculate the change in electric potential energy when the magnitude of the electric field is 250 newtons per coulomb. All right, the starting position is 2.5 meters from the origin, and the final position is 4 meters from the origin. All right, so let's see here. So this particle is being, again, it starts off at 2.5, just like our proton did in our last example, 2.5 meters away. Then it's being pushed outwards, or not pushed outwards, but moved outwards, I guess you could say, to 4 meters. So again, our delta D here, we have a change in 1.5 meters. Okay, some of the other things we have, again, we have our charge there. It's the exact same magnitude as a proton, but just negative this time. So the power of negative 19 coulombs. And this time our electric field's a little stronger than our last one. It's 250 newtons per coulomb. All right, and we want to find the change in electric potential energy, which again, I'm going to use that formula that we had. The change in electric potential energy is equal to negative Q times epsilon times delta D. All right, now if I substitute in, okay, so we got our negative sign there. Our Q value again is negative 1.6 times 10 to the negative 19. All right, our epsilon, let's plug that in, it's 250. And again, our delta D is 1.5. All right, so I got a negative times a negative. That's going to give me a positive, then times a positive. It's going to give me a positive times a positive. So we're going to have some positive electric potential energy, an increase in it. And again, it's because these two are attracted to each other. So as we pull a negative charge away from the positive plate, it's again like a spring where you're expanding the spring, so it's pulling back on you. And if I multiply these three numbers, I end up with 6.0, let's see on my calculator here, times 10 to the power of negative 17 joules. And so again, what's happening is our EE, our electric potential energy, is increasing because, well, it is attracted to the positive plate, or because the electron, is attracted to the positive plate. Now, I don't know what was happening to this charge, but the bottom line here is if it is moving, that must mean then that the EK is decreasing. So perhaps this particle, there's a chance that this particle, this electron, is slowing down. Because our EK is getting, is decreasing, as I mentioned up above there. All right, so our EE is increasing because, again, it's like a spring where we're pulling these two things that are attracted to each other apart. But again, if in the case that maybe this electron was moving away from the positive plate, that attraction would slow that electron down. All right, now we get to the second part. So it was moving apparently. In B here, it says determine the initial speed of the electron. All right, so now we're going to find the initial speed. There's the mass of an electron, assuming it has come to rest after the displacement has occurred. So before, in our last example, we let this positive go. It started at rest, and because of they were being repelled, it took off. This one, the electron was moving away from the plate at a certain speed, but because of the attraction, it was slowed down and it came to rest. So again, either way, what we have here is conservation of energy. Our change in electric potential energy, all right, which in this case is increasing because we're pulling these charges apart, plus our change in kinetic energy is going to equal 0. All right, now our change in electric potential energy, I'm going to leave that number for now, but there it is, 6.0 times 10 to the negative 17. I'm just going to write that here. All right, there's our change in energy. We'll put that in after. Now, our change in kinetic energy. Again, we have mass. Now, the change in kinetic energy means there's a change in velocity, where if you're looking for a change in velocity, you take your final minus your initial, but they're squared in our kinetic energy formula. All right, and again, don't forget about the divided by 2. And it all equals 0. Now, it has come to rest, this electron, which again means our VF is equal to 0. It's come to rest. All right, so what I can do here is get rid of, I don't want to change that sign on that, so we'll get rid of the VF because it's 0. All right, and let's clean this up a little bit. Our VI is negative, and our mass is multiplying it, so let's make sure we put that back. There we go. All right, so we have the mass, we know the change in electric potential energy, and what we're going to find here is the negative VI squared, or the VI squared, I should say. All right, so again, our change in electric potential energy is 6.0 times 10 to the power of negative 17, positive. All right, now this negative sign here, I'm going to move it and combine it with the positive sign. Opposite signs becomes negative. Our mass is 9.1, 11 I should say, times 10 to the power of negative 31. And I move that negative sign with the positive sign, so it becomes negative. And then we have this VI here, squared, and divide by 2. And again, it equals 0. All right, so again, I want to simplify things. So I'm going to move this negative, this whole term here. Whoops. I'm going to move this whole term over to the other side of the equal sign. So when it changes side, it changes sign. So I don't have to rewrite all that. Here's what we're going to do. Now I'm going to become positive. And there we go. It's moved sides. Okay, so next up, what are we going to do here to simplify things? Well, I guess one of the easiest things, like I did before, I'm going to multiply both sides by 2. And so those 2's divide each other out, and on this side we end up with, let's see here, 1.2 times 10 to the power of, ooh, I got to look at that, my writing there. What was that? That's a negative 17. That's a bad 7 there. So let's put a 7 in there, make sure it looks right. Okay, and so let me see here. I take that 6, make sure I get my right answer here. 6.0 times 10 to the power of negative 17. And then multiply by 2. And I get 1.2 to the power of negative 16. And again, that's equal to 9.11 times 10 to the power of negative 31. We got some very small things we're dealing with here. Times VI, the initial velocity squared. All right, so then next up I'm going to, again, I want to get VI by itself, so I'm going to divide both sides by this 9.11 times 10 to the power of negative 31. And what I do to one side here, I'm going to do the other. Okay, so those divide each other out. And we're down to VI squared here. And let's see, we take our 1.2 times 10 to the power of negative 16, divided by 9.11 to the times 10 to the power of negative 31. And I'm getting, let's see here, 1 point, again down to 2 decimal places, 32 times 10 to the power of 14. All right, and again, to get rid of that little 2, we're going to have to square root both sides. And so my initial velocity of my electron, because it was moving, let's see here, square root my answer. We end up with, let's see here, where's my answer button? Oh, there it is, and I end up with 1.15 times 10 to the power of 7, and again we're using our standard units here, and so it is meters per second. So again, this is the initial velocity we found where the electron was moving away from the positive plate, but again it was attracted to the positive plate, which slowed it down and eventually stopped it, in fact, this as an example B. But again, the law of conservation of energy, whatever you lose or gain electric potential energy is what you're going to lose or gain with kinetic energy. And that is a look at electric potential energy and the movement of particles.